Alright, today we're doing the notes on 10.6, the Law of Cosines. I really like this section. Earlier we've been just doing right triangles, and often you're really limited in what you can do. Most triangles aren't right triangles. And now with 10.6, Law of Cosines, 10.7, Law of Sines, we're able to go through and solve for any triangle, whether it's a right triangle or not. And first thing though is, in order to get the equations to work out right, we need to make sure that we label the triangles correctly. So that's why I have Roman numeral 1 labeling triangles. And for those, the angles or the vertices of your triangle, those all have to be caps. So in capital letters, and typically we just go through and do A, B, and C. So I'm going to put down a capital A, capital B, capital C. It doesn't matter where you start, which direction you go, you just kind of pick and go from there. But now as we do sides, the sides, those are going to be lowercase letters, so lowercase, and they have to be the same as the opposite angle. So it didn't matter where we started with our capital A, B, and C, assuming you're doing angles first, but now this side here must be lowercase c. Lowercase because it's a side, C because it's opposite angle C. Down here on the bottom then is going to be lowercase letter A, and over on the left for mine, lowercase letter b. Had we started in a different spot with our capitals or went in a different direction, that's going to impact directly what the different sides are. So labeling triangles, the angles, always capitals, sides, lowercase, and angles and sides, same letter, have to be across from each other. Law of cosines is this first one. And law of cosines, I wouldn't draw this triangle here, I'm just kind of trying to make a point for this one. But if we were to go through and have this be a right triangle, so just really trying to show where law of cosines comes from to kind of demystify it a little bit. But if we'd had a right triangle here, we could say we have A, and then my next side I'll call B, and my last side I'm going to call C. And if you remember back to Pythagorean Theorem, we could say that C squared is going to equal A squared plus B squared. And that would work, or A squared plus B squared equals C squared. Now, that's going to work for any right triangle, but now the question was, what happens when we don't have a right triangle? So if I take this same one here, and I'm going to kind of copy it and throw it back in that same spot. But now let's say I change my angle. So I'm trying to have the length be the same, but I'm changing my angle. Actually, I'll put it up a little bit higher. So I'm taking that one, and then, well, I'll just get rid of this one now. So we'll get rid of that. Now, if I have my red one, if I take and slide this up but try to keep it the same length, you'll notice now that this red isn't long enough anymore. Now that I don't have a right angle anymore, or right triangle, that red's not long enough. What we have to do is we have to put this little correction factor on there, so I'm drawing that in green, which kind of makes up for the fact that we don't have a right triangle anymore. That's really where law of cosines comes from. This correction factor here is something that we add into the Pythagorean theorem. And it's going to be minus 2ab times the cosine of capital C. C being this angle up there. So this here is law of cosines. It looks bad, and a lot of times people get intimidated by how it looks, but if you're labeling your triangles correctly, it's really not that bad to work with. So C squared equals A squared plus B squared, and then minus our correction factor, 2ab times the cosine of C. This is going to work really well if you're trying to find angle C, or if you're trying to find side C. But sometimes now we're going to be looking for angle B instead, or side B. So you could take the same thing and have it be B squared equals instead of C squared equals. And if you look at this top one and kind of see the pattern, it makes it a whole lot easier. Where here we have C squared equals and then A squared plus B squared, kind of the other two variables. If we were to copy that here with my B squared then should equal, if you think, well, what do the other letters have to be? That's going to be A squared plus C squared. Now we get over to this correction factor. We have minus 2, and then AB. Those are going to be the two sides that are over here to the right side of the equals. So for B squared equals, it's going to be minus 2, but instead of AB, it'll be A and C. So minus 2AC times the cosine of my only capital letter. So when it's c squared equals, when we're looking for this side, it's going to be angle c across from it. Now that we're talking about b squared this side, we need to be talking about angle b. So times cosine of capital B for angle B. The last one then, sometimes you're looking for angle A over here on the right in my triangle, or side A, so we'd have a squared equals. I'm going to pause for about 3 seconds, give you a head start, try to fill in what the rest of that equation would be. Alright, so I'm going to fill mine in now and see if I can catch up to you. So a squared equals, it's going to be the other two letters, so b squared plus c squared, minus 2 times b and c, so 2 times b times c, times cosine of capital letter A. Alright, so what kind of triangles can you use these for? Technically you can use this for a right triangle also, it's just a whole lot more work. So when you get a right triangle, perhaps on a quiz coming up soon, please use the SOHCAHTOA, it's just a whole lot easier. But for these, if you think back to geometry, your triangle congruence theorems, one that law of cosines is going to work really well for is when you have a side angle side triangle. So I'm going to write SAS. Is how we abbreviated them. An example, I just kind of drew a random shaped triangle. Say you know that this here is 8, this side here is 7, and this angle maybe is 50 degrees. That if you have one like that, law of cosines is going to work really well for finding this side here, called the x. The other one that it's going to work for is the side triangle. So had we known that maybe this side here is 7.5. Now that we know the three sides, side, we can go through and find any of those angles. So that's going to be the things that law of cosines works really well for. And it makes sense if you think back to your other congruence theorems, and I wouldn't write these down, but we had angle, side, angle, we had angle, angle, side, were the other two. Well, the two triangle congruence theorems that you know more sides than angles is what law of cosines works with. And if you look at the equations, we have all lowercase letters all through here. So all 3 lowercase letters, and we only have 1 capital letter. So there's only 1 angle. It makes sense then that an equation that's made mostly up of sides is going to work best for the triangle congruence theorems that have mostly sides. So I want to do an example, 2 examples, one of each of these, and that rounds out the notes from this section. So first example, maybe pause the video a sec and quick scribble down this triangle here. And I'm going to go through and label it now. So it doesn't matter where we start with our capital A, B, and C or which direction we go. I'm going to go around this way, so A, B, C. If you label yours the same as mine, it'll just be easier to do the example. Now it matters what we pick for 10. 10 has to be lowercase, it's a side, and angle A is across from it, so 10 is going to be side A. And 13 then is going to be a lowercase b because it's across from angle B. And now if we're looking for a side, I should put an x in here. We're trying to find this, which now is going to be side C. So going back to my equations, the equation that's going to work best is going to be this top one. 1, because we're looking for side C. 2, because it has angle C, and that's the only angle that we know. Alright, so now we start by writing out the equation. So c squared equals a squared plus b squared minus 2 times a times b times the cosine of capital C. Writing out the equation is going to make it a lot more likely you get it right. And also then when I ask you to know it from memory for the test, you don't need to cram the night before the test. You will have been getting them right and you'll know it by the time we get to the test. So, alright. So a squared then is going to be a 10 squared plus b squared, so 13 squared. And now it'll just be 2 times those two numbers, so 2 times 10 times 13 times the cosine of 23 degrees. So if I go through and punch this into my calculator, so 1, make sure you're still in radian mode, but now I could say I have 10 squared plus 13 squared minus 2 times 10 times 13, and then cosine 23 degrees. If I punch all that in, I come up with 29.7, I'll say that. And a lot of people, they get to this point and they're like 29.7 and they're done. But if you go through and look, we didn't just find C. It doesn't make sense that this side here would be 29, almost 30 long. That's impossible with this side being 10 and this side being 13. So if you had kind of copied your work down every step, that'd be a good reminder that it's C squared equals this. So to go through and get your actual answer, you need to go through and square root that. And like always, please don't round till the end of a problem. So if you do square root and then your answer key, it'll actually put in all the decimals there and you'll get a much more accurate final answer of 5.45. And if we look then, so C is going to be 5.45. That makes a whole lot more sense. That if this is, well, if that one's 10, this is about half that, ideally be a little over half that, we're probably right. Some of the triangles I draw, I'm just kind of shooting in the dark for what the angle is, so don't take that too much right. But if you have something like 29, there's absolutely no way it could be right. All right, last example. Next example is going to be a little bit tougher. Finding an angle. Nice part is the setup is all exactly the same. So we start with putting in our capital A, B, and C. You might want to pause the video quick a second and copy it in. But here's my triangle A, B, and C. Now my 3 is going to be side A because it's across from A, so lowercase letter there. 11 on the top is going to be lowercase c because that's opposite angle C, which then leaves 10 should be lowercase letter b because that's all that's left, and sure enough it's across from angle B. Now we need to find an angle, and it doesn't really matter which one we do. Maybe I'll pick angle B. So I'm going to put my theta right there and say we're trying to find theta. Now for which one we use, we're looking for angle B, so if you go back to where I had my 3 equations, we have to use the middle one. That's the only one that has angle B. So we go with b squared equals, so b squared equals a squared plus c squared minus 2 times a times c times cosine of capital B. And now that we have that, we can just kind of plug and chug. So my b squared, well, that'll be 10 squared. You could write in 100 if you wanted to. Equals a squared, so 3 squared, or 9, plus c squared, so that's going to be 11 squared, or maybe you just write 121 right away. I like doing it 3 squared, 11 squared, because now I can just say, well, it's 2 times 3 times 11. 2 times this number times that number, times cosine of capital B. So you could leave it as a capital B, you could put in a theta, our variable for an angle. It's up to you. Now here's going to be where people make the mistake. That people go through, and if you get one like this wrong, it's almost always the exact same thing. People go through, they punch all these numbers into their calculator to come up with one number times cosine of theta. And that's not legal, that's not allowed. And the reason is this. When you do order of operations, you have to multiply, that right there, before you can subtract. We can't multiply 2 times 3 times 11 times cosine of theta because we don't know cosine of theta. So because we can't multiply this section here, we can't do this subtraction right now. What we could do is take and combine these two numbers together. So I have 3 squared is 9 plus 121. So I could say that that's going to be 130. That's totally legal. We could take and do 2 times 3 times 11, so we'd have 33 times 2, so that's minus 66, times the cosine of theta. And we could do the left side, we could say, well, 10 squared is 100. So far we haven't done anything wrong. Now it's tempting again, people will go, and the 130 minus 66 is kind of like begging some people in their mind to go through and do that problem. We can't do that yet, because we can't do the subtraction until after we've done the multiplication. We can't multiply, so we can't subtract. So now the steps are always the same. Once you get here to solve one like this, or you could say combine those two, combine these three, then your next step is going to be to start pulling things from the right side over to the left until we're just left with a theta. So like normal, when you're solving for a variable, we start with doing order of operations backwards. So we start by subtracting 130 from both sides. That'll give me a negative 30 equals, now we always are going to end up subtracting because it'll always be a positive right there because it's a couple side lengths squared. It has to be positive. We'll always be left then with this minus sign, so negative 66 times cosine of theta. So now we need to move that negative 66, and it's tempting to add for some people, but look at how it's connected. It's connected with multiplication. So we're going to divide by negative 66. And this is where I'm going to flip over and start using my calculator. So what's left then on the right side is cosine of theta. And if I punch in negative 30 divided by negative 66, so I have negative 30 divided by negative 66. I'm going to get a decimal. Yeah, it's kind of a pretty one. So 0.45 repeating. So if I go over here, I have 0.45 and the 45 is repeating. Now in a moment I'm going to use my answer button just so I don't have like rounding error there. But our last step is we need to get rid of the cosine. We want to just have theta by itself. So to do that, it's kind of like we had the angle theta, we did cosine to it, and we got this decimal. Well, we undo cosine by doing the inverse cosine, just like we did back when we were looking for an angle in a right triangle. So inverse cosine will cancel that out, and we're left with theta on one side. And if I do inverse cosine of my answer, then I'm not rounding before the end. So second, then my cosine button, second, and then negative to pull up the answer. And I get 62.96 degrees. I was always taught to round to one decimal point. I'm just going to round then to 63.0 because the 6 makes the 9 round up. So then that would be theta is 63.0 degrees, or 63.0 degrees. And that's probably of law of cosines today the toughest question, and including law of sines, the one we're going to do tomorrow, the other way to find angles and sides in non-right triangles. This is the toughest one, so if you can remember the steps on this, you should be golden. That's it for law of cosines.